Today we're going to learn about covalent compounds, how they form, and also how we name them. Because covalent compounds are, again, not as complex as ionic compounds, so we don't really have the difficulty in naming them. Okay? So, as we already discussed, a covalent bond is an atom that is held together by the sharing of electrons, as you can see here. They are made up of two non-metal atoms, and we call them molecular bonds. A molecule is just a neutral group of atoms joined together by a covalent bond. So this is an example of H2O. Your oxygen is here, hydrogen, hydrogen, and these pieces here are the bonds, covalent bonds that are holding it all together. So I'm going to flash some words at you, or some compounds, sorry, at you. And based off of our previous understanding of ionic and covalent bonds, I want you to tell me whether or not each compound is ionic or covalent. Remembering that ionic bonds are a metal and a nonmetal, and covalent bonds are two nonmetals. Sodium chloride, ionic or covalent? Perfect. If you said this was an ionic bond, you are absolutely correct. Sodium being a metal and chloride or chlorine being a nonmetal. What about nitrogen and phosphorus together? Would we call this ionic or covalent? Perfect. So if you picked up on the fact that nitrogen and phosphorus are both nonmetals and you said that's covalent, great. What about copper chloride? So we're really getting the hang of this. It's pretty easy once you figure out what type of element each atom is, whether or not it's metal or non-metal, to tell us whether or not it's ionic or covalent. Next one, potassium bromide. Great, if you said that was ionic. Phosphorus mononitride. This one might be a little tricky because I don't think you guys have ever seen anything like this last guy down here. Give it your best guess. So if you said covalent, you were right. Phosphorus here is a gas, and then if you don't know what you're looking for here, but you picked up on this nitri part, that's nitrogen. And nitrogen we know to also be a gas, which means this is covalent. What about this guy? Okay, perfect. Again, another ionic compound. Two more over in that bottom left corner. What is that? Sulfur and oxygen together make a covalent bond. And last but not least, these two here. Perfect. Yes. So magnesium sulfide is an ionic bond. Great job, guys. Now we're going to watch a really quick video that just kind of explains ionic bonding and covalent bonding using these very cute dogs. And then we'll move on to naming covalent bonds. Okay, great. So that was cute. And hopefully it helped you guys who are. Tower Defense 6 video game soundtrack by Tim Haywood. Sure. Okay, Google, stop. Wow. So guys, don't ever have Google Homes because they are very disrespectful and they interrupt you a lot. Um, yes. So, this is a very cute video, and hopefully this helped you guys who are more visual learners really understand the concept of covalent versus ionic bonding. Okay, so how do we how do covalent bonds share their electrons? How do they trade electrons? So in forming covalent bonds, atoms share electrons to obtain the full valence shell like a noble gas. Okay? The goal is to hit the octet rule. The octet rule basically just means that electrons or atoms want to form groups of 8. Okay, they want a full valence shell of 8, and that's what they're going to do. They're going to match up with other atoms that hit that 8 count. Okay, so in this example, we have H2O. This is what this is. We have H2O, and oxygen only has 6 valence electrons, while hydrogen only has 1. And so 2 atoms of hydrogen will hook up to 1 atom of oxygen so that hydrogen can have a full shell of 2 and oxygen can have a full shell of 8. And then over here, you have carbon, which only has 4 valence electrons, represented by the blue, and more hydrogens, hydrogen atoms, which have 1 electron or valence electron each, which is denoted by the red. And they're going to hook up with one another until each hydrogen atom has 2 valence electrons or access to 2 valence electrons, and carbon has access to 8 valence electrons. That is the whole point. They want to share electrons to obtain an 8 count valence shell, or in hydrogen's case, or other atoms, or in hydrogen's case, a 2 count shell. There are types of bonds within covalent bonding: single, double, and triple. Your single bonds are just 2 atoms held together by the sharing of 2 electrons. Your double bonds are atoms held together by the sharing of 4 electrons. And then your triple bonds are atoms held together by the sharing of 6 electrons. So this here is an example of a single bond. Here, you're looking at a double bond. And I'll wait for that image to go down. This one here at the bottom is a triple bond. The lines, the number of lines in the Lewis structure indicate the type of bond. A single line is a single bond, a double line is a double bond, and a triple line is a triple bond. As you go down the list, the bonds increase in strength. Think of it as if you are trying to hold something together with string. If you only have one string, it's definitely not going to be as strong as three strings, essentially. What are the properties of covalent bonds? They have low melting points and low boiling points, and they have no electrical conductivity. They suck at producing electricity. They are the chemical formula of a covalent compound is called a molecular formula, and the molecular formula just shows the exact number of each element in the compound. So an example of this would be carbon, hydrogen, carbon with 2, hydrogen with 6. Okay? So how do we create a name? How do we create a formula for covalent compounds? Well, covalent compounds are made up of two or more nonmetals that have bonded together. And to name them, we use the Greek prefixes. You have to memorize these because they are not on any reference sheet. You have to memorize these. Luckily, you know some of them, and the others should be kind of familiar to you, or you can think of a quick trick. So 1 is mono, 2 is di, 3 being tri, like tricycle, 4 being tetra, maybe like Tetris, is how I think of it. 5 is penta, like the pentagon with 5 sides. 6 is hexa, like a hexagon with 6 sides. Heptagons have 7 sides, so hepta is the prefix. Octa, like octopus with 8 sides. Nona, like 9. Both of those words start with N. And then deca, which is 10, and we're already familiar with deca as like decade or decagram if you remember your metric units. So to actually name them, you're going to write out the first element, like fully write it out. Then you'll place the Greek prefix before the word. And then you just repeat that same process for the second element. You change the ending of the second element to IDE, and then you combine them into a name. Important note, only the second element in a compound can start with mono. The first element can never have the word mono in front of it, even if there is only one of that element. So for example, here we have a compound containing sulfur and oxygen, and I was avoiding naming them previously properly, so I would just point out the elements because I wanted to get to this part so we could actually understand why. So I have 2 sulfur atoms, and we know that 2 is the Greek prefix di. So I would just write di in front of the word sulfur. And then I have 3 oxygen atoms. So I would write tri in front of the word oxygen. Then I'm going to get rid of the ending of oxygen, that YGEN, and change it to IDE. So it becomes trioxide. And so the final compound, the final name would be disulfur trioxide. Now to go from the name into the formula, you simply write the chemical symbol of the first element. You place the prefix number behind the symbol as a subscript, and then you just repeat it with the second element and smush them together so they form a formula. So for example, tetrachlorine octabromide. The first element is chlorine. The chemical symbol for chlorine is Cl. The first prefix is tetra. Our Greek prefix chart tells me that's 4. The second element is bromide, which is bromine. So that's Br. And then that octa we know is 8, like octopus. And then you just combine all of that together into a formula. Cl4, Br8. Perfect. Simple, easy peasy. So go ahead and get some practice in. If you need to use it, the name chart is here, but please remember that you have to be familiar with these. You must memorize them. So don't become too reliant on this chart. And we will work through this, or we will talk later. Sorry.